I'm Miss Nyaplan. Nice to meet you. I'm happy to see everyone on the Super Memory for Schools program. Today, I will accompany everyone in Lesson 4, the relative position of a straight line and a circle. Our lesson today revolves around two main contents. The first content is the three relative positions of a straight line and a circle, and the second part is the relation between the distance from the center of the circle to the line and the radius of the circle. Let's start with the first part. Here, we have an image of the sun and the horizon. The position of the sun and the horizon tells us three relative positions, the line and the circle. Let's observe and tell me how many points do the line and the circle have in common. In the first image, the line and the circle have 2 points in common. In the second image, the line and the circle have 1 point in common. In the third image, the line and the circle have no points in common. The question arises whether a line and a circle can have more than 2 points in common. If a line and a circle have more than 2 points in common, the circle must pass through at least 3 collinear points, and this is impossible. Therefore, a line and a circle can only have 2 or 1 points in common, or even none. In the first image, a line and a circle have 2 points in common. We call that the line intersects the circle. The first relative position is the intersection of a line and a circle. So, from the above image, tell me, when does a line cross the circle with center O? Line A crosses the circle with center O when they have 2 points in common. Then, line A is called a second, and the 2 points A and B are called the intersection points. I called OH is the distance from O to the line A. In the first image, line A passes through center O, so H and O coincide. The length of the distance OH is 0, meaning that OH is smaller than the radius R. In the second case, line A does not pass through the center O. After drawing OH, we see that OH belongs to the right triangle OHA, and because it is the right side, it is smaller than the hypotenuse OA. Thus, we get OH is smaller than R. Therefore, when a line intersects a circle, we get OH is smaller than R. Besides, as AH belongs to triangle OAH, which is right-angled at H, applying Pythagorean theorem, we have OA squared equals OH squared plus HA squared. Thus, we have HA equals the square root of OA squared minus OH squared, meaning that HA equals the square root of R squared minus OH squared. I call it thesis 1. On the other hand, the circle center O has AB as the chord and OH perpendicular to AB at H. We have H as the midpoint of chord AB according to perpendicular relationship between diameter and chord. From that, we have HA equals HB, and this is thesis 2. From 1 and 2, we get HA equals HB equals the square root of R squared minus OH squared. Thus, when the line intersects the circle, OH is smaller than R and equals to HA equals HB equals to the square root of R squared minus OH squared. We have the second position. The line is the tangent to a circle. We have the drawing. In this case, the line touches the circle with center O if they only have 1 point in common. A is called the tangent line of a circle with center O, and C is called the point of tangency. I called OH is the distance from center O to line A. So, we get H is coinciding to C, and we see that OC is perpendicular to the line A, and the straight line OH equals R. Thus, we have the theorem that if a line is the tangent line of a circle, it is perpendicular to the radius crossing the point of tangency. Here, if we have A is the tangent line of the circle center O and C is the point of tangency, according to the theorem, we have A is perpendicular to OC at C. Coming to the third position, the line and the circle do not intersect. Based on the drawing, we have line A and circle O do not have any common points. We say line A and circle O do not intersect. We call OH is the distance from O to line A. Thus, we have OH is greater than R. So, from the three relative positions of a line and a circle, we move to section 2, the relation between the distance from the circle center to a line and its radius. In the first drawing, we have line A and circle O intersect each other. We set OH equals D. From that, we have D is smaller than R. And in return, if D is smaller than R, we have line A and circle O intersect. Thus, this is a bidirectional property. In the second drawing, we have line A touches circle O. From that, we have D equals R. In return, if D equals R, we infer that line A and circle O touch each other. In the third drawing, we have line A and circle O do not intersect. From that, we infer that D is greater than R. And in return, if D is greater than R, we infer that line A and the circle O do not intersect. Thus, from the three above comments, we have the relation table of the distance from the circle center to the line and the circle radius as followed. When a line intersects a circle and they have 2 points in common, we have D is smaller than R. When a line is tangent to a circle and they have 1 point in common, we have D is equal to R. The third case is that when a line does not intersect a circle and they have no point in common, we have D is greater than R. We shall base on this table to solve the following problem. Fill in the blanks of the table with R is the circle radius. D is the distance from its center to the line. Here, we have the circle radius with distance D, a number of common points and the relative position of a line and a circle. Let's fill in the blanks on the table. In the first line, we have the radius R equals 5 centimeters and D equals 3 centimeters. As we have D is smaller than R, the number of common points between two objects would be 2 points. Thus, the line intersects the circle. In the second line, we have radius R equals 6 centimeters and 1 common point, meaning that D is equal to R, so D equals 6 centimeters. Thus, we said that the line is tangent to the circle. In the third line, we have radius R equals 4 centimeters and D equals 7 centimeters. So we have D is greater than R. Thus, we have no common points and the line does not intersect the circle. In the fourth line, we have D equals 4 centimeters and the line is tangent to the circle, meaning that D is equal to R. So, we have R equals 4 centimeters and the number of common points is 1. In the fifth line, we have radius R equals 7 centimeters and D equals 7 centimeters, or D equals R. The number of common points between the line and the circle is 1, and in this case, the line is tangent to the circle. We have already finished the given exercise. We continue to answer question number 3. Given a line called A and a point O, which is 3 centimeters from line A, drawing a circle with a center O and its radius of 5 centimeters. Section A. What is the position of line A and circle O? Why? Section B. B and C is called as the point of tangency of line A and circle O. Calculate the length of BC. Here, I also draw line A and point O, which is 3 centimeters from line A. And OH is the distance from O to line A. I draw a circle O. Its radius length is 5 centimeters. We set OH equals D. We have R equals 5 centimeters. OH equals D equals 3 centimeters. So we have D is smaller than R. And as D is smaller than R, we infer that line A intersects circle O. Thus, we get the relative position of line A and circle O. Next, we solve section B. Calling B and C as the intersection points between line A and circle O, calculate BC. Here, we have B and C as the intersection points between line A and circle O. Calculate BC. To calculate BC, we observe that BC is a circle chord that does not cross its center. And we have OH is perpendicular to BC at H. So, we have H is the midpoint of the line segment BC. We apply the perpendicular relation between the circle diameter and chord. So, to calculate BC, I shall calculate HC and multiply HC by 2. We get the length of the segment line BC. To calculate HC, we must use the triangle OHC, right-angled at H. According to Pythagorean theorem, we have OC squared equals OH squared plus HC squared. We swap sides and get HC equals the square root of OC squared minus OH squared and replace the length of the segment lines, we find HC equals 4 centimeters. From that, we infer that BC equals 2 times HC equals 8 centimeters. So, we have just finished problem number 3. By large, in today's lesson, we need to remember the following 3 main knowledge. We have the first case where a circle intersects a line. When that happens, there are 2 intersection points, and line A is called the second line, and D is smaller than R, and the second position is that A line is tangent to a circle. When that happens, there is 1 intersection point, and line A is called the tangent line of the circle. C is called the point of tangency, and we have the relation of D equals R. In the third case, the line does not intersect the circle, so the number of intersection points is none, and we have the relation of D equals R. So, our today lesson has come to an end. Thank you for listening carefully. I wish everyone a happy and nice day. See everyone next time in the Super Memory for Schools program. Goodbye.